extra half an hour by Francesco Fucito. He'll finish the stuff that he couldn't finish yesterday. And we'll also have small discussion about this writing competition that we'll have for students. They will write for the best lecture notes. So if there's any questions, how things will happen, so we'll discuss it after this second coffee break of today. And we'll have poster session after that. Now we have Ami Hanany. We will continue his lectures on D-branes and supersymmetry.
Okay. Thank you very much. Yesterday we do this brain system. Let me just make a reminder. You have two NS brains, and I don't remember which colors I used. Maybe it was orange for the D3 brains. So let's put D3 brains like that. And I have N of them. We made a statement that this system has two interpretations, which gives me a very non-trivial correspondence between two moduli spaces, which are of interest in both quantum field theory and in string theory. So the first point is that we see here n SU2 monopoles. And the second point is that we see an n equals 4 3D, n equals 4 super Young-Mills theory with an SUN gauge group. Actually, it's a UN. In this particular case, the U1 decouples, and this corresponds to an overall degree of freedom, which is the center of position of those three branes. So we get this correspondence, and we also said that when you have such a system of 2NS and D3, the vector multiplet with 16 supercharges decomposes to the vector multiplet with 8 supercharges and the hypermultiplet with 8 supercharges. And the boundary condition is such that this one stays and this one gets projected out. Whereas if I'll have a different, now let me introduce a new set of branes. I'll denote them by blue. I'll put D5 branes and the 3 brane in between. This will give me the other boundary condition. So let's call here NS, and here for the D5, the boundary condition is doing the reverse. So this one gets projected out, and this one stays. Okay? Any questions about this point? So this is very useful because it gives me a collection of building blocks to construct a gauge theory as I wish. And so I'm going to introduce the following notation. We will have a quiver. And the quiver is going to have two objects. Actually, you could call it a graph, because I'm not going to have any arrows. Quiver typically has arrows in it. In the graph that I'm going to use, there are no arrows. there are two objects, there are nodes, and those nodes come in two types, circle and square, and there will be edges. So edges connected nodes, connect nodes, and we are going to have some dictionary between a brain system and a quiver. So here's a brain system. I'll take a collection of several Neve-Schwarz 5 brains. Let's call them, let's say there are K of them. And in each segment, I have now K-1 segments. And so in each segment, I can stretch a collection of 3 brains. And each segment will have its own brain number. So we'll call it N1, N2, and Nk-1. Larger. So this one is too small. Okay. So those are labels, right? So those are labels of the indices. So I just use a convenient labeling system which will tell me which interval, which segment I'm using. And so the translation would be to assign a node with a label N1 to every time I have 3 brains between an S brains. And an edge, each time a Neve-Schwarz 5 brains separates a collection of 3 brains. And this is going to be Nk-2, and the last one will be Nk-1. Right, so we have a nice correspondence. This is a physical system of brains in space-time. And this is a mathematical object, combinatorial object, if you wish, which tells me how the brains are arranged in space-time. Now, on top of this, what I'm going to do is to assign for every node I'm going to assign a vector multiplet. So this is going to be representing a Lagrangian. And for this particular construction, it's going to be a Lagrangian in 2+1 dimensions. With 8 supercharges, or what is called n equals 4 in 3 dimensions. So every node is a vector multiplet, every edge is a hypermultiplet. I can think of fundamental strings, let me do it over here. If I have an Navier-Schwarz 5-brane and a collection of 3 branes ending on one side and another collection ending on the other side, then I can stretch a fundamental string across 2 sides of the Navier-Schwarz 5-brane, and this gives rise to a matter field which transforms under the gauge group which lives over here and the gauge group which lives over here. So if I'll collect, every such string can end once on each of the branes on one side and once on each of the branes on the other side, and it gives rise to this hypermultiplet, which we denote by an edge. But we further say that how do we construct the Lagrangian? We write down all of the kinetic terms for the fields which live in the vector multiplet, all of the kinetic terms for the hypermultiplets, and because of the amount of supersymmetry, all of the interactions are fixed by the form of the representations. So this quiver is a synonym, if you want. It's a shorthand notation for writing down a Lagrangian. Any questions about this point? Whenever I write a V, it's going to be Neumann, and whenever I write an X, it's going to be Dirichlet. So intuitively, what you have is that when the 3-brane is stretched between 2 Navier-Schwarz 5 branes, it's not allowed to move away. Otherwise, it will either break supersymmetry, or it has to end on something. This is just a segment. So you cannot just leave a segment without ending on anything, right? So it's just forced to end on the Navier-Schwarz 5 brane, and the Navier-Schwarz 5 brane is located at this position and not in another. So all of the positions transverse to the Navier-Schwarz 5 brane and are also transverse to the 3 brane must be projected out. Right? So that's the intuitive picture. That's right. And so, and the 5 branes are oriented in a different way. I didn't mention this point. I could just make a list over here. So we're taking a convention where the Navier-Schwarz 5 brane are stretched along the, well, let me write it over here, 0, 1, 2, 4, 5. So these are the directions of the Navier-Schwarz 5 brane. Then the 3 brane is stretched along the first 3, but another direction, which we will call 6. And then the 5 brane is stretched along the same directions as the 3 brane, 0, 1, and 2. So this is where the space-time theory lives. And, or the, well, maybe I should call it not space-time, but the world volume theory of the 3 brane lives in those 2 + 1 dimensions. And in 3 more, 7, 8, and 9, right? So all of these directions, 3 up to 9, are the direction of the moduli, the scalar fields, which live either on the 3 brane or on the 5 branes. And each one of them serves, gives a different role in terms of the theory that lives on those 3 branes. Any questions about this point? So now before I continue, we will introduce more objects into the quiver, but before we do that, we already get a very nice result. One of the results. Since I picked K, the Weschwarz 5-brane, I have UK gauge theory on the world volume of the Weschwarz 5-brane. For which, if an observer lives on the Weschwarz 5-brane, he sees the 3-brane as magnetic monopoles. They carry magnetic charges. So I'll have a monopole configuration or monopole solutions of type N1, N2, all the way up to nk minus 2 and nk minus 1. Magnetic monopoles are associated with the root of, when at Hooft and Polyakov wrote the solution for the classical solution, they used a particular root. They did it for SU2. There's only one root, positive root, and so they assigned the monopole solution to this root. When we have a UK gauge theory, there are k-1 simple roots, and those k-1 simple roots are associated with the magnetic charges. So we would say that the magnetic charge of the monopole solution is divided into those k-1 different components. And so the result that we get is that the moduli space of this SUN or UK gauge theory monopoles well, I just call it a single monopole with these particular charges. The moduli space of this UK monopole is the moduli space of the quiver that we wrote over here. N1 up to nk minus 1. So this is a nice generalization. Any question about this point? So I should say, since from the point of view of the three-dimensional theory, we have scalar fields in vector multiplets which get vacuum expectation value each time the brane is in a different position. The moduli space, I should stress here that it's the Coulomb branch and not the Higgs branch of this theory. Okay? It's the set of vacua that this Lagrangian admits, right? So when we write down the explicit terms of the Lagrangian, there will be a potential term, and I'm going to look for the solutions, the set of solutions for zero potential, and this is going to be characterizing a single vacuum. And it is known that the Coulomb branches receive many quantum corrections, and we want to be able to figure out what are those quantum corrections. And here we are lucky enough to have that we could turn the problem into a classical problem of finding the moduli space of classical monopole solutions. It's all encoded in the quiver data. So because of the supersymmetry, the potential is fixed by the by this data. We can be explicit in case. Yes. Well, you do. If you want, I mean, if you accept that I have a Navier-Schwarz 5 brane, and now let me draw this string, so I'll need a different color. Do we have a different color? I'll get a green color, right? So I'll take a D string. Green is invisible. Yeah, I mean, I guess, can you distinguish this from a white? So this is a D string, okay? This string is allowed to end on a Navier-Schwarz 5 brane. The end of the D string is a point particle, and again, I can apply the Gauss law. I do it in the same reasoning that I do for any system where branes end on branes. And if it's allowed to end, this must imply the existence of a gauge field living on the world volume of the Navier-Schwarz 5 brane. This is a type 2B Navier-Schwarz 5 brane, and so I say that there is a gauge field, there are all of the scalars, they form together a super representation of the theory in 6 dimensions with 1,1 supersymmetry that has the massless degrees of freedom as a vector multiplet. Okay? So the Navier-Schwarz 5 brane of type 2B has a gauge theory in 6 dimensions like any other gauge theory that we know. It's different than the Navier-Schwarz 5 brane of type 2A. Because there, the basic object which ends is a D2 brane and not a D string. And the D2 brane gives rise to strings living on the world volume of the Navier-Schwarz 5 brane. More questions? These are very important questions, so please keep on asking them. So the next thing that we will do is to add extra ingredients. We have Navier-Schwarz 5 branes, we have D3 branes, we have D5 branes. I'm going to put these type of objects, and in the figure that I'm drawing, I was not specific about it, but in those directions that we are having over there, the horizontal direction represents the direction 6, where the 3 branes are stretched, but they are intervals, and the Navier-Schwarz 5 brane are point-like. On the other hand, this direction, I'm going to draw it as representing 3, 4, and 5. It's an R3. And so the Navier-Schwarz 5 brane spans along this direction. So they will look like lines. The 3 branes also look like lines, horizontal lines, except that they are segments. Whereas the D5 branes are point-like in both 6 and 3, 4, 5. So they look like points. So I'll use a blue chalk, and I'll just place a collection of 5 branes in each such segment. And now I'm going to have another addition to my quiver data. So suppose that I have this system to an S-branes. Here's a D3 brane, and here's a D5 brane. There's going to be a fundamental string. All colors are visible. So you have a multitude of branes, and this gives me the richness of those systems in type 2B. And this one has one end on a 3 brane, another end on D5 brane, and it extends my quiver to have additional hypermultiplets, but now those hypermultiplets are charged under the gauge symmetry, which lives on the 5 brane. And if I have, I'll just need to say how many of them there are. So let's put another number. Let's call it M, M1, M2, MK minus 1, right? Are these large enough, those labels? Not so much. So since I have M1, the 5 branes, I will have M1 options for the fundamental string to end, and this will correspond to a link over here, an edge, with label M1. And here, M2, and so on. MK minus 1. So I extend my quiver to include, it has 3 types. So the brane system has 3 types of branes: Navier-Schwarz 5 brane, D5 brane, and D3 brane. And they each play a different role. The D5 branes give rise to the flavor symmetries in this quiver. The Navier-Schwarz 5 branes separate one gauge group from another and give rise to those edges. For each Navier-Schwarz 5 brane, I have one edge. And whenever 3 branes and 5 branes are within the same segment, I'll get another edge. Any questions about the way I draw this quiver? And again, each such quiver is a Lagrangian. So I have a whole family of gauge theories which characterize the low energy physics, the relevant physics of this brane system. Mm-hmm. It's not so useful in this picture. You'll have to possibly compactify the space-time. It's less nice. So let's just discuss the nice things, and then get to more complicated things. Next point that I'm going to do is to, well, here's a quiver. What can I do with such a thing? I mean, can I really solve the features of such a brane system? So what I'm going to do next is to consider the following brane system. I'm going to take a specific example with one 3 brane and n D5 branes. It's a particularly simple system, by the rules that we wrote down, this is going to look like the gauge theory with U1 gauge group and N flavors. This is super QED. In, let's be specific, 3D, N equals 4 supersymmetry. Okay? So the simplest possible theories that we study quite a lot could have a very simple representation in this brain system. And super QED has, has one gauge field. We have scalars in the vector multiplet. So I can give them vacuum expectation value, and they will be called, they will form the Coulomb branch. And I can count how many. We have 3 scalar fields, which parameterize the position of the 3 brane along the Navier-Schwarz 5 brane, and so I have 3 of them. So 3 scalars. Also, if you recall the talk on N equal 2 supersymmetry on representations, this was done in 4 dimensions. So vector multiplet contains 2 scalar fields in 4 dimensions, but in 3 dimensions it contains 3 scalar fields. So it's very consistent with what we heard. And there is another very interesting feature, which is very special to 3 dimensions, that a gauge field can be dualized to a scalar field. So it carries 1 more degree of freedom. And so the vacuum expectation value of the scalars can be given also to this dual of a gauge field. So altogether we have a Coulomb branch which is 4 real dimensional. 3 scalars plus 1 dual photon. Any questions about this point? So the dual of the photon is a scalar field, and it can admit a vacuum expectation value. 3 of those scalars are easy to see in the brain system. They are just the position. The 4th one, the dual of the gauge field, is harder to see. It's not the position of a brain. So we will settle just by looking at 3 out of 4 scalar fields. On the other hand, we have scalars in hypermultiplets. There are n of them. Each hypermultiplet contains 4 real scalars. And so I have 4n real scalars. But now I need to recall, if I give them vacuum expectation value, they will give a mass to the gauge field by the Higgs mechanism. So 4 of them will be taken away in order to be absorbed into the vector multiplet to form a massive vector multiplet. So the dimension of this moduli space is going to be 4n minus 1. And traditionally, this is called the Higgs branch, whereas the previous moduli space is called the Coulomb branch. Any questions about this point? Let's try to see how we form the Higgs branch. Yes, so this I determine by the boundary conditions. Right? So by when a 3 brane ends on a Navier-Schwarz 5 brane, the vector multiplet survives. The boundary condition, the hypermultiplet is frozen. And so what we see here, we see a single brane which is allowed to be anywhere, and therefore it characterizes the Coulomb branch. How do we see the Higgs branch in this system? So I'm going to move to a new coordinate frame. Instead of drawing it in the 6, 3, 4, and 5, I'm going to draw the same brane system in the directions of 6 and 7, 8, 9. How does this look like? So I have n D5 branes. Let's first start with the D5 branes. Along 6, they are point-like, and along 7, 8, 9, they are stretched. And so they look like lines. And how many of them do we have? N of them. What about the Schwarz 5 brane? It's localized in 7, 8, 9 and in 6, so it looks point-like. So I will draw it like here and here. And the 3 brane is stretched all the way. So this is the same brane system, still the Coulomb branch, because the 3 brane is stretched between 2 Schwarz 5 brane. But I'm going to do another trick now. When I look at this here, well, let's first look in this figure. I could always align the 5 branes to be hitting the 3 brane. What happens at this point? I get an extra massless state. The hypermultiplet, which corresponds to the fundamental string between the D5 brane and the D3 brane, becomes massless. Let's write effective masses. In order to write down the effective masses, I'm going to use a BPS formula. Central charge which takes the form Z. Z is a triplet that's set by the n equals 4 supersymmetry. So I'll just denote it by a vector. And it's going to be the, let's denote phi, the scalar field in the vector multiplet. And by M, the scalar field, which is denotes the position of the D5 brane. So here I have every 5 brane can have its own position in the 3, 4, 5 directions. So I will have parameters mi, the masses, and I will have the position of the 3 brane, which is phi. Both phi and mi are vectors in the 3, 4, 5 direction. And what I wrote here is just the distance. Well, not yet the distance, but this is the difference of 2 vectors in 3 space. Whenever the D5 and the D3 touch, the central charge becomes 0, and the mass of a hypermultiplet becomes 0. Okay? Any questions about this? So I have a very nice physical picture of this brane system. Yeah, it's I here runs from 1 up to n. So the most general formula for the central charge takes all vector multiplets that you have, background and dynamical, and it looks like a sum over Qi, let's call them Qi, times phi I, where phi is a generic term for all scalars in vector multiplets, and Qi are charges. In this particular case, I'm talking about a fundamental string which is stretched between a D3 brane and a D5 brane. So it carries charge 1 and -1. So more generally, I will need to figure out what are the charges under each of those U1s that are members of the vector multiplets that contains those scalars. Any question? So what I can do is to set all of them to 0. What happens when I set them to 0? Now new directions open up, right? In this configuration, the 3 brane can just move, can be up and down, but whenever they touch, something new happens. They look like this, and now they can split. So let's maximally split this. I have n segments, and therefore I have n plus 1 different, sorry, I have n d5 branes, and therefore I have n plus 1 different segments. So the Higgs bunch is going to look like this. And now the 3 branes can be anywhere. Any questions about this point? Let me just throw it all the way to the end. Okay, I maximally split the D3 brane into n plus 1 different segments. We recall that the dimension of the Higgs branch is n minus 1. I have n minus 1 segments between D5 branes, and I have 2 more between D5 and NS. Now, let's consider this system between D5 and NS. This is an interesting system which has no degrees of freedom. No, it's just corresponds to the Lagrangian is the same. Whenever we place the branes in a different configuration, we are just picking a different vacuum, right? So it's a single Lagrangian, the single quiver, but many vacua. It's an excellent question. I'm not changing the Lagrangian. I'm just picking the vacuum of my brane system, of my quantum field theory. The potential is set by the supersymmetry. So I write it once and for all. Once I have the quiver, you want to think of it as solutions of supergravity. You'll first have to find the solution itself. It's a very complicated solution. As far as I can tell, the best which was done is to take all of the charges to be large and to write down fairly complicated brain systems. There is a work by a group in UCLA which did it, but they will have large charges because a supergravity solution must have large charges. And there is a continuation of this story by the Colnormal people. So there's been quite a lot of activity. I'm not going to use it. I'm here just characterizing the effective field theory which lives on the brain. I'm not writing supergravity solutions. So this is related to the question of Jorge yesterday. He likes to think about this system from the point of view of supergravity, which is very important. The approach that I'm taking is to think about this system as the effective field theory which lives on the brain. And I want to extract all possible information I can get just by thinking of it as an effective field theory. Right? So I'm setting the supergravity solutions aside, and I'm just thinking about the gauge theory that lives on those brains, trying to extract as much information as possible. It is a conceptual point. It takes time to get used to that. This is the way of thinking I'm using, and I will show how much extra information you could extract just by taking this approach. Okay? We are seeing it as we go. You see that it's a very different way of thinking from the way you think about it as a supergravity solution. In fact, if you try to compute the moduli of the supergravity solution, it's going to be quite a hard task. Whereas here for us, it's just, it corresponds to figuring out the different positions the brains can admit. Okay, so it becomes pictorial rather than heavy computational. Yes. Already stable. There are no forces. Thank you for this comment. Yes. All of these brain systems, there are no forces. The amount of supersymmetry is high enough such that there are no forces. If I take this brain system, the force between the D5 and the NS is 0. The D5 and a neighboring D5 is also 0. D5 and D3, 0 forces. Which is quite a challenge to show if you look at those supergravity solutions. Because the supergravity solutions that cannot tell a single brain unless you put it a very high charge. More questions? Okay, so here's what I do. I set yes. There are corrections to the Coulomb branch, but not to the potential energy. The potential energy stays 0, right? So we have a single vector multiplet in this particular problem. And I have 3 scalar fields, 1 dual photon. They all have 0 potential. And they are going to get affected by the presence of those hypermultiplets. We will see, hopefully we will see the explicit description of this Coulomb branch. We are getting there. No, it's not. So we will have to introduce the notion of monopole operators. We didn't discuss them so far. And monopole operators are behind the notion of Coulomb branch corrections. we talked about classical monopole solutions, but they are very different from monopole operators. And in a sense, they will it's a good question. So the description that we will have, well, in this particular, let's wait and then try to discuss this point, because there are several things that I did not introduce yet, and so if we want everybody to be following, then we will have to introduce some few more points, if we will have the time. So, more questions. So we are at the point of identifying. Remember, the Higgs branch has n-1 times 4 different moduli. We recall that for the vector multiplets, we could see only 3 positions. And so that's the same thing is going to happen. And so we are going to count n-1 different segments, which correspond to 4 moduli. So I have n different branes, n-1 different segments, and there are 2 more, which I was about to discuss here. So let's discuss this system first. In this system, there are no moduli. For a simple reason, because the boundary condition on one side removes half of the degrees of freedom, the boundary conditions on the other side remove the second half, and I'm left with no degrees of freedom. So intuitively, what it means is that the 3-brane is not allowed to move along this direction because the 5-brane is not there, and the 3-brane is not allowed to move outside of the board because the D5 brane is here on the board and not away from it. Okay, so there are no moduli, and therefore, when I count moduli, I only see n-1 of them. So this is the description of the Higgs branch. And it has dimension. And from now on, what I'm going to do, I'm going to remove this 4, because all of the moduli come in multiples of 4. I'm going to count in a quaternionic way, which is n-1. So we have a 1-dimensional Coulomb branch and an n-1 dimensional Higgs branch. Okay? Any questions? To proceed, we're going to compute the Higgs branch using the F and D term equations. And now we're getting close to the lectures by Francesco, because Francesco was telling us about the ADHM construction. And this is the ADHM quiver for the 1 SUN instanton on C2. Francesco did not show a quiver in his lectures. He showed the equations instead of that. And it turns out that the equations that he wrote down can be derived as equations which follow from this particular quiver. Let's try to see how we get those equations. And now I'll need to introduce a superpotential W made out of 3 fields which I need. I'll call them phi. Phi is complex. So related to the phi that we have over here, phi is a triplet here. I'm going to pick 2 out of 3 scalars and complexify them. So it's a complex variable. And I'm going to introduce hypermultiplets contain 2 chiral multiplets. We saw this in the lecture on supersymmetry. So I'm going to introduce 2 quark fields, which we will call Q and Q tilde. This is the traditional name. This is 1 by n, and Q tilde is going to be n by 1. So it's a vector and a covector with complex entries. Altogether, I have 4 times n real degrees of freedom. These are the 4 scalar fields, 4 n scalar fields, which represent the degrees of freedom of fundamental strings between D5 and D3 branes. Any questions about this point? There was a question about interactions. Out of those 3 different fields, the superpotential takes a cubic form, and it looks like I'm going to be careful about the dimensions of these vectors. So I'm going to have phi, q, and q tilde. Right, so phi is 1 by 1, just a complex number. Phi times q, this is an ordinary matrix multiplication, again matrix multiplication, and there's no need for a trace. This is a complex number. This is the way the superpotential looks. And I've set the masses to 0. Why did I set the masses to 0? Because the Higgs branch is maximal when all the branes coincide, right? I put all of those branes on top of the 3 brane. So I set masses to 0. Let's try to compute the F-term equations. The F-term equations, I'm going to be particularly interested in the Higgs branch. So I'm going to differentiate W with respect to phi, and this gives me Q times Q tilde, and I set it to 0. So I have a single complex equation which takes a vector and a covector, takes the dot product between them and sets them to 0. Let's now write down the gauge invariant operators. And I mean chiral. Limit, I don't take the Q bars, I only take the Qs. Holomorphic. So chiral is the same as holomorphic. So what kind of gauge invariant operators can I write down? I'll call it a matrix M, which is just the product of Q tilde, and be careful about the order. Q tilde is n by 1, Q is 1 by n, and therefore M is n by n. And this is naturally called the Meso Matrix. It's an n by n matrix, but since it's made out of vectors, it has maximal rank at most 1. Right? Recall your knowledge from linear algebra. These are matrices of rank of maximum 1. Could be 0, in which case the Meso matrix will be just the 0 matrix. But at most, the rank is 1. Any questions about what we are doing? Okay, so let's proceed. Let's compute the square of this matrix. The square of this matrix is Q tilde, Q tilde, Q. Again, the square is an n by n matrix. But look at this equation. Q times Q tilde is equal to 0. It's here, and so this is 0. And so we find that the Meso matrix not just has rank at most 1, it also squares to 0. And it's gauge invariant, right? Because Q carries charge +1 under the gauge group, Q tilde carries charge -1, so M carries charge 0. So this is the set of gauge invariant operators, and the moduli space, the Higgs branch, becomes is the set of n by n matrices. We also can show that trace of M is trace of Q tilde Q, which is Q times Q tilde, and it's 0. So the set of n by n matrices such that the trace is 0, the square is 0, and the rank is at most 1. Any question about this derivation? It's a simple application of the F and D term equations. The D term equations are included here by just restricting to the set of gauge invariant operators. This is a moduli space which is known by the name of the nilpotent orbit because the square is 0. So it's the minimal nilpotent orbit of SLN. And here I'll put closure. So this is the description of this moduli space. What we've just done is to derive, because recall these are ADHM quivers, we derived the moduli space of one SUN instanton. Any question about this? So now we get a beautiful connection between the stuff that we are doing and what we heard in the lectures on supersymmetry, what we heard in the lecture by Francesco on instantons. Think about it. If you have any questions, please go ahead. That's not a trivial material. I'm sure you have questions. Just make sure to come and ask. We are here. So take the advantage. So here was a piece of small computation which characterizes the brain system that we have. And now I'm going to represent a new quiver. So I'll call it the second quiver, the magnetic quiver. And when we wrote down this quiver, we gave rules. We said that whenever we have the 3 branes between the Weschwarz 5 branes, I'm going to assign a node. For every Weschwarz 5 brane, I'm going to assign an edge. And for a set of the 5 branes in a given segment, I'm going to assign another edge with a square node. But what is so special about D5 branes and NS branes? Both of them are 5 branes. Both of them have 3 branes ending between them. So let's try to reverse the order. I'm going to call the magnetic quiver a quiver where the 3 branes, instead of being stretched between the Weschwarz 5 branes as here, I'm going to use this quiver where the stretch between the D5 branes. Here's the example of the quiver that we had. So I'm going to assign by the same analogy. Whenever we have a D3 between D5, I'll get a node for each D5. I'll have an edge, and whenever I'll have a set of NS, I'll get a square node and an edge as well. So let's see what kind of quiver we can read from this system. So I have n-1 different segments, which will correspond to n-1 different nodes. Each one of rank 1. Soon I'm going to assign a gauge theory to this quiver. I have n-1 nodes, and they are connected like that. For every segment, there is a node. For every D5 brane, there is an edge. We just need to take care of the last two. And here I have a brane between the Weschwarz 5 brane and the 3 brane. And so I'll get a flavor node here and another one over here. Any questions about the derivation of this quiver? And so perhaps that's the point to mention about the brane creation. Maybe I should go back. Let me mention it over here. Brane creation. The brane creation phenomenon says that here I have a particular arrangement of NS and D5, but if I switch the order along the 6th direction, there will be an annihilation of a brane. Okay? So the brane creation, if you want, is the step where if I move the NS5 brane past the D5 brane on the other side, I'll get a brane creation. And conversely, I'll get brane annihilation if I take this 5 brane, move it over here, and this brane will be annihilated. We could give various arguments for this effect. It's a very important effect. So if I take this system, let's use this brane creation phenomenon, I could map this brane system to a set of n-1 different 5 branes, and I'll move this brane inside. I'll get a brane annihilation. And I'll move this brane inside. Again, I'll get brane annihilation. and all of the other segments will be still there. From which I can get the quiver that we said up there. Right? So those are two different brain systems which lead to the same quiver. Any questions? So this corresponds to the fact that that there are no moduli between those branes, and the order is important, right? So I'm not able to avoid passing this 5 brane. If I pull it, I'll break supersymmetry. I'll have to move through it. And so this, if you look also in the directions here, you see that there's only one common transverse direction to the Navier-Schwarz 5 brane and the D5 brane, the 6th direction. So they cannot avoid each other. And the term for this is that those branes are linked. Right? The NS and the D5 are linked. And if they are linked, there is the brain creation phenomenon. So if I have a configuration like this, right? So what does it mean that they are linked? They form a very particular ordering in the 6th direction, such that if I change the order, like in here, I need to pay some compensation for this. And this compensation is the brain creation mechanism. The linking here also implies that there is a magnetic charge that the Navier-Schwarz 5 brane induces on the D5 on the Navier-Schwarz. And in order to preserve this magnetic charge, I'll have to have this brain creation. And we could discuss this in detail. I mean, it's just that it's stuff from mid-90s. I just wanted to mention it rather than derive it in detail, unless you insist that I will do it. More questions? Okay, so what's the bottom line? We have a set, the same brain system gives rise to 2 quivers. Here's one, and here's the second. Given this quiver, let's try to compute the moduli space of this one. I'm going to have the same set of rules. I'm going to compute the Higgs branch. And the Higgs branch in this particular quiver, I'm going to use a notation for each edge. Each edge represents a hypermultiplet, and therefore it has 2 chiral multiplets assigned to it. So I'll call the first one U1 and D1, the second U2 and D2. And those in between, I'll call by the names of L1, R1, all the way to L. And notice that we have n-1 nodes, so n-2 segments. And so the last one will be n-2 and R n-2. I need to write down the superpotential. And the superpotential is going to take the form, for every edge, I'm going to have two terms. It's similar to what we had here, except that we set the masses to 0. So over here, for a square node, I will have no term. But for a round node, I will have a term. So I need one more piece of data. I'll denote the scalar fields in each of the nodes by phi 1 up to phi n minus 1. Okay, so the first term is going to be phi 1. And then U1, D1. So this is for the first edge. Now I'm going to have, for the second edge, minus phi 1. Actually, yes, that's fine. So phi 1, R1, L1. And then for the, so that's for the first node. For the second node, I'll have the term which goes to the left and terms which goes to the right. So it's going to be phi 2, L1, R1, minus phi 3, R2, L2. And it's going to continue like that all the way until the end. Let's just write down the terms, the last term over here. I'm going to have phi n minus 1, L n minus 2, R n minus 2, minus phi n minus 1 times going up and down. I hope I didn't make a mistake. We'll have to check it later. But what do I get from this system? So I wrote down the superpotential. And as we said, for every edge, there are two terms. If in addition we set the masses to 0, then I remove one term here and one term here, first and last. So once I have the superpotential, I can write down the gauge invariant combinations. And I see that there are 3 types. So gauge invariance here I need to require with respect to n minus 1 different gauge fields. So I must make a gauge invariant. Let's do the simplest. So if I take U1, well, I'll take D1, U1, that's gauge invariant because they are only charged under the flavor symmetry. But actually they are even charged 0. And I can also write L1, R1 and Li, Ri. But what I'm going to show, we're going to see that if I differentiate with respect to phi 2, I'll get that R1, L1 did I make a mistake? I think I made a mistake. So I think I should have done it. yeah, phi 1 will go up and down, and will also go right and left. Oh, I see. Sorry. And here there should be a 2, right? So when I have, so let's do it again. So phi 2 first goes left and right, and then goes right and left. But the indices change. So I think this is correct. So please check me if I've done it correctly. So when I differentiate with respect to phi 1, I get the equation that u1 d1 is r1 L1, but since those are complex numbers, they exchange. So this is equal to this, equals to this. There is only one invariant out of those guys. So it's a matter of being patient and showing this. Try to do it as an exercise. The other gauge invariant starts from the left and goes all the way to the right. So let's call this this guy Z. This one X starts from down, R1, R2, all the way up to R n minus 2, and then going up. And the last guy is going the other way, starting from the right, going all the way to the left. So I'll go D2, L n minus 2, L n minus 3, all the way up to L1, and then going up 1. Okay? So I have 3 gauge invariants, X, Y, and Z. And I use the F-term equation to show that when I take a product of 2 chiral multiplets of the same edge, they are all the same by the F-term relations. But now what I can do is to compute the relation X, Y. It's D1, the product over R, U2, D2, the product over L, and then U1. And again, I can use the F-term relations and show that U2, D2 is equal to, is again one of these Z's, and I just need to count how many of them there are. I'll find that there are n of them. So convince yourself that this expression is equal to Z to the n. So the final equation looks like a set of 3 variables which satisfy one relation, otherwise known as the geometric singularity C2 mod Zn. Any questions? So we computed the Higgs punch of the magnetic weaver. The next point that we want to make is to compute the Coulomb branch of the electric weaver. And here's the point where we were asking what are the quantum corrections that we can have. But we actually already have the answer with us, because if I will start with the brane system here, and I will declare this to be my theory, right? So this is my Lagrangian. The magnetic quiver for this quiver is going to be the quiver that we started from. So this notion of electric and magnetic is self-dual. So the magnetic quiver for this one is this, and the magnetic quiver for this one is this one. So in fact, the Coulomb branch of the electric quiver is the Higgs branch of the magnetic quiver. And vice versa. It's a very important correspondence. Any question about this point? If you don't ask questions about this, you asked in the same time. Go ahead. Yes. Yes. Mm-hmm. Yes, that's right. Yes, yes. No, it's going to be the same quiver diagram. So we are staying with the same Lagrangian, and with this. Yeah, so it's it's a billion dualization, so I can do this. I can just replace every abelian gauge field by a dual photon using a process of dualization, which is a Gaussian integration. If it was non-abelian, we would ask some questions. How do we do that? But here we are lucky that in n equals 4 supersymmetry, because there is always a joint matter in vector multiplets, the vacuum configuration abelianizes the gauge group, right? Because every W boson is going to be massive at the point where the branes are separated. You could still ask the question, what happens when the branes are coincident and then the W bosons are massless? But luckily, again, in n equals 4 supersymmetry, and then that's something to get used to it. I mean, there are some various arguments, but the abelianization persists even at the non-abelian points. There are other effects that we need to take into account, which involve monopole operators and dressing factors, but we still didn't develop the tools for looking at this, right? So I wasn't sure whether people here know about the Higgs branch, and from the fact that I don't get questions, it seems like people don't know about the Higgs branch. So we first need to figure out that, or at least to make sure that people understand how to compute the Higgs branch. So we did 2 examples here, and I would encourage to do a few more examples just in order to be sure that you understand how to compute Higgs branches. Once we get this out of the way, we could start thinking about computing Coulomb branches, because they involve some quantum corrections, a collection of further assumptions. They don't just follow from vacuum equations of Lagrangian. And you had a question. The second example is not an ADHM system. Right? So the ADHM statement says that the Higgs branch of this quiver is the moduli space of one SUN instanton. If you compare with the, so he used different notations, but when all the dust settles, you'll find that it's the same description. Here we specialize to the case of one SUN instanton. Francesco is interested in any instanton number, and so we'll have to generalize this picture. But again, for simplicity, we first need to understand the one instanton and then try to generalize to higher instanton number. The ADHM statement does not make any claim about the Coulomb branch of this quiver. The Coulomb branch of this quiver is the Higgs branch of this quiver, which we just computed to be a simple space, an orbifold of C2. And it doesn't fall into the theory of instantons. It's not so relevant. I mean, we could see how this system arises. It is a gravitational instanton, yes. It's correct, but what is the question? Yes. In this picture, it's not so visible. We could have an alternative picture where all four directions are present. It's not easily visible in this picture. We'll have to dualize this picture in order to see all the clear interpretation as an instanton. There is such a system where there is a clear interpretation as an instanton, but we did not discuss it. And it was not discussed in Massimo's talk. It was not discussed in Francesco's talk. So I can give you the answer. It's just you'll have to consider a different brane system where you take a D6 brane and you take a D2 brane and you try to write down the quiver associated to this system. When the D2 brane is inside the D6 brane, it's a codimension 4 object and is interpreted as an instanton. So in this picture, it's not so visible, but over here it does. Okay, and the quiver looks like this. One for the D2, N for the D6, and another fundamental string for the D2 strings, right, which decouple. In our system, they are not relevant. They carry charge 0. They do not interact. So they just form a free hypermultiplet, which has the physical interpretation of the position of the brane or the position of the instanton in C2. So the relevant part of the quiver, so after I remove this adjoint field, I get to this quiver up there. And I have now the statement that the Higgs branch of one theory, I mean, it's the same quiver. So the Higgs branch of this system is the moduli space of instantons. So not always I have the right interpretation that I want. In different brane systems, I'll have different interpretations. But when I do the actual computations, I get the relevant results. You could do T-duality and relate it. You were asking for joint fields. Oh. We have election campaign on the outside. But you're asking how those two guys relate to each other by T-duality. So under T-duality, the D6 branes become D5 branes. And I'll have n of them. The D2 brane becomes a 3 brane. And I'll draw it on a circle. And that's it. So if you'll try to write down the gauge theory, living on this system, you'll get this particular quiver. This is the Higgs branch picture, but if you draw the Coulomb branch picture, then it will look like this. Except that this lives on a circle, so it will give you precisely this quiver. Okay. Thank you.